Again, my name's Austin Roche. I'm a software architect at MapleSoft. I've been working for Maple since 2007, but before that, I was a student researcher working with Maple and doing research since about 1997. Maple has a rich history of differential equation solving. In fact, it's been on the forefront of computer algebra solving of exact solutions for differential equations for, you know, ever since I've been involved anyway. So in my PhD research and my undergraduate research was also involved with finding new algorithms for solving differential equations. So I'll just get started on showing the kinds of things that make Maple unique as a tool for helping to teach differential equations. So just to start off, I'll start off with something kind of visual. I'll just go to this first section. We have something in the so this is, by the way, this is maybe a new GUI, and I'm showing the Maple 2025 interface, and it looks a bit different than maybe what you've seen in previous Maple releases. One of the interesting things is we have an education tab here, and if you click on it, there's a differential equation section. And you can do D plots, and I'll just show the ODE analyzer here. So you can click on it and you can type in some equations. I'm going to quit out of that and instead write the differential equations directly into the worksheet and put my cursor there and right click and open the context panel for more. And I didn't click in the right place. Here we go. Solve DE interactively, and again brings up that ODE assistant. Now it's got the differential equation that I input there, and what you can do, you can solve it symbolically. It asks you a bunch of questions on how to do that. Example, show the Maple commands, and let's see. Oh, press the solve button. Well, there's the solution right away. I'm going to go back and then do solve numerically. Oh, I need to put some conditions. So let's see, y at 0 is equal to, say, 0. Add that condition. And let's add the condition that y prime at 0 is equal to 1. And add that condition. And then done. And then solve numerically. And it asks a bunch of different algorithms and stuff. I will just do the default and plot it, and there you see the plot. There's a number of different options here. I'm not going to go through all of them. You can also run this command interactively from the command line. Let me just close this context panel. And go to the next. Okay, this I've done already. So just to make things easier going forward and to make things look nicer, there's a special command PD tools declare. And what it does is y of x will now be displayed as y. Most of the examples I have will be involving y of x as the solving function. So, okay, I need to refer to this equation above. So that'll be, I didn't factor this here. This equation 1.1. If I refer to that equation 1.1, and you can see the notation is a little more compact. Instead of y of x with a diff notation, we now see that it's just y subscript x to indicate a double derivative with respect to x. And then I can go further and say derivatives with respect to x will now be displayed as prime notation, and it now looks like that. So that's just showing you the kind of textbook-like notation that we can get. We invoke this kind of syntax. Now, I'm going to talk about DE tools and PD tools quickly. DE tools is a package that has, as you can see, 132 commands that you can use. A lot of them are quite abstract, a bit advanced, so not so much for teaching with. So just to show an example for the dplot command, this example is involving Newton's law of cooling. So there's the differential equation here. I'm just going to execute that, and some parameters are set. And here's some initial values. And let's see what dplot does. So it shows it's got the direction field in the background, then it's got some solution curves. There's obviously many different options to adjust the display there. There's also a phase portrait command that just shows the solution curves, and a dfield plot command that just does the direction field. For more, that's kind of the visual numerical solutions. Now, if you look at if you want to look at the symbolic solutions, dsolve is the main command in Maple to do that. And it's a very advanced command. It's got all the latest research behind it. So again, I'm not going to show the help page here, but here's some examples. So just a simple ODE, dsolve gives you a solution. You can also provide initial conditions and solve them together, and it'll find the values of the integration constants and simplify. You can see now instead of exponentials, it's got a hyperbolic trig in this solution. Here's another solution involving, it's the same system, but solve it using a Laplace transform. Again, it's getting the same solution. ODE test is a command that what it's doing is testing that solution is correct. So it's comparing the solution, plugging it into the original differential equation, checking that after simplifying left-hand side minus right-hand side that you get 0. It's also doing the same for the initial conditions, plugging in the solution, applying the initial conditions and checking that those are satisfied as well. Can also ask for series solutions, and it solves systems, and so on and so forth. dsolve also has a numeric option, so you can, for example, output a procedure that you can plot numerical solutions and stuff like that. I'm not going to show that because that's more advanced and not typically used in teaching. I'm going to get to the more teaching aspects coming up. ODE advisor, again, I'm not going to show the help page. This is a command that kind of tells you what class the given differential equation can be categorized into. So for example, this particular equation is classified as a Bessel equation. And then I'll show you some other useful commands. Here's an example of a third order ODE. You can find the integrating factors for it. It finds 2 of them. And just taking the first one, we multiply it by the ODE, and then we call ODE advisor. And one of the things that it shows, it classifies the resulting equation as exact. So what we've done, we found an integrating factor, multiplied it through, and then the resulting equation is exact, which means that if you take left-hand side minus right-hand side, that resulting expression is a total derivative with respect to the independent variable. And then in that form, you can then call the firint command, that's short for first integral, and then solve for the highest derivative. And so you get this kind of reduction of order and then solve for the highest derivative. And it looks like that. And then if we just call desolve, it'll solve the whole thing, the remainder, and it'll get this general solution involving 3 integration constants. And then again, we can test that and make sure that it's the correct answer. There's also the PD tools package. That's, again, more related to partial differential equations. I'm not going to go into that in a lot of detail here, but there's a lot of different commands in there for manipulating partial differential equations. In particular, PD solve is a really important command. It can solve basically all the commands and that you can do find exact solutions for. So the heat equation, stuff like that. Again, I'm not going to show the help page for that right now. Next, I want to go on to student ODEs. This is a special subpackage that's designed for teaching essentially a first course on ordinary differential equations. So there's many different commands here, and there's some sub packages as well. So I'll go into those. For example, the first ODE I have here, it's a first order differential equation. And if we have a command to isolate the highest derivative, and then we can find an integrating factor for that, and we can separate the variables. That's essentially, in this case, just multiplying by the integrating factor. And then we have an integrate command that just integrates both sides with respect to the given dependent or independent variable. And if we go back to the original equation that I started with, this is a simple harmonic oscillator. Again, showing some simple commands, take the differential order. These are useful for students. Change variables, so you can change the independent variable, multiply it by the imaginary constant, and it changes. So instead of having trig solutions like you would have for this one, so you get trig solutions. Now for this one, you're going to get exponential solutions. And just show some more commands here. Solve I showed already. The type command, there's a few things that it can check. It can check if it's exact, if it's separable, and if it's linear. And then you can test again. These are all there's some related commands in the top level Maple, but these are all kind of designed to be easy for students to use. And then this is a really interesting one, ODE steps. So what it does is, given an equation, let's just show that equation again. Where is it? 410. So that's this one that I'm highlighting here, the harmonic oscillator. If you type on ODE steps, it'll go through and output a list of steps to show the solving process. So let's solve this equation. highest derivative means the order is 2. Isolate the second derivative, group terms on the left-hand side, and then you can get the characteristic polynomial by taking the coefficients. And the differential operators translates to the variable r. And then factor that, the characteristic polynomial, find the roots, get the first solution, second solution, and then just take a linear combination of those, and that's a general solution. And then we just plug in the actual values of those solutions, and we get the final solution here. So that's a very simple version of the OD steps command. We also have a number of specialized examples in student ODs solve. That's a sub-package of student ODs. So these are essentially solving methods. We have a number of them. So Bessel, by Laplace transform, by perturbation, by series. So essentially solve by Laplace transform, solve by perturbation, and so on. Undetermined coefficients, variation of parameters. We have a Cauchy-Euler, which is a certain type of ODE that can be solved, and the Chebyshev and exact first order linear, high order. So those are all kind of just based on the differential order. And then linear constant coefficients and second order separable, solve. Solve is again a sub package itself. Oh, so that's referring to this whole, yeah. So there's this solve command in the solve sub package. And then system, you can solve a system of ODs. So I'll go through a few of these and show how they work. So here's a good example for a series solution. And you can just call the command by series, or you can add the extra option output equals steps, and it'll produce the steps. And just before I execute that, you could equivalently just call OD steps on the original ODE, and it will also produce the steps. And in this case, it finds it's not, you're not specifying method when you do it like this. So just looks for the best method it can find. In this case, it also finds the series method. But I'll just show the steps here. So for example, let's solve this. So assume a series solution. Rewrite the DE, the ODE with series expansions. So in this case, we're taking this term here, x times the derivative dy dx, and writing it as a series. Notice, yeah. Okay, so we already have y here. So x times, yeah, you have to take a derivative, so you get an extra factor of in the first term in that series, well, with k equals 0. No, it's just if I copy this, show. Oops. K has a value here. I need to unassign k. There to go. And if we take a derivative of the above with respect to x, okay. And then now we need to multiply by x. Oops. To just do that once. Okay. So that's where this is coming from. The x's cancel, so I would need to simplify that. Should work. No. Line. There we go. So that's where this formula down below comes from. It's first taking a derivative and then combining the extra factor of x back inside. So instead of x to the k minus 1 times k for the derivative of x to the k, there's an extra x now. So it's x to the k again times x times k. And then the ak is still the coefficient there. And then you do the same thing for the second derivative, and you get this value. And then because that's the power there of the x is k minus 2, we need to shift that. So all the values of k change by adding 2 to them. So we get this different coefficient. And then put all those, we have the sum from k equals 0 to infinity of x to the k times, and this is the coefficient of x to the k. And then we take that coefficient and set it to 0 because all the terms in the series have to be 0 on the left-hand side because they are on the right-hand side. You get this equation, and then you solve the recurrence relation, and you get this solution. Okay, so moving on to the Laplace transform example. Set up an ODE and some initial conditions, and we can just ask for the solution in terms of by Laplace transform, or we can ask for the steps as well. And I'll just show very detailed steps. So it's repeating the initial, the original system. Defining notation for the Laplace transform of x of t is capital X of x. And then applying that, it's a linear transform, applying that to the original ODE here. So apply the same on both sides. Use the linearity to apply to each term individually. And then there's some rules for the Laplace transform that are invoked here. You plug in those values to the equation above, and you essentially end up with this algebraic equation for capital X of x here. And then you collect terms, factor, and solve for x of x. And you get this solution. Something's not simplifying here, but that's okay. Everyone still understands what's going on. And then we take the inverse Laplace transform, and yeah, so that's a bit of an involved step. We have to do some manipulation. It's doing that manipulation to get it into a form that's recognized. And then it recognizes these two terms go to these forms, e to the minus t times cos of t and minus e to the minus t times sine of t. And then you plug those in and essentially evaluate, and that's your answer. So it's showing all the steps. By perturbation, this is the perturbation method. So plug in, so we enter a differential equation with a epsilon parameter in it and some initial conditions. And then we use the perturbation method. And I'm not going to show the output, the steps output for this, but you can do that as well. It's really involved. Undetermined coefficients. So this is where you're looking for a particular solution to the ODE, and you have a certain guess as to the form. So it just returns the answer, and we can ask for the steps here. It's instructive to go through this. So we're solving this equation, determine the form using the method of undetermined coefficients. So we know it should be, we have sine and cos in the forcing function and its derivatives. So we make a guess that it's some linear combination of those two. And we substitute that into the original equation, and we get this. and then we match the coefficients of cos of x, match the coefficients of sine of x. We get a system of equations, and it solves them multiplying by the inverse of the coefficient matrix, and essentially multiply that out, and we get the answers for the coefficients, and we just plug those into the answer. So there's some more involved examples on the help pages. Variation of parameters. Here's an example. You can use all different types of inputs for this. So here I'm going to use an input involving matrices, and a vector forcing function, and a vector for the dependent variables, and set up the actual system. The derivative is equal to the coefficient matrix times the dependent variables plus the forcing function. And then you can just ask directly for the solution and we'll provide that to you, or you could ask for the steps. And again, this is quite involved. So for example, let's solve this equation. Well, it first shows you that you need to find the eigenpairs for the coefficient matrix. It's computing that in one step. So the eigenvalue, one eigenvalue is -1, and the eigenvector associated with that is -1, 1. The other eigenvalue is 4, and then we have an eigenvector 2/3 and 1. And we take the first of those eigenpairs and get the solution to the homogeneous system from that eigenpair, and use the second one, get the solution for that one. That's just plugging it into the formula, essentially the different values here. And then we create the fundamental matrix from those two. So we multiply, so we multiply the solution times two different coefficients and put those in a matrix. That's called the fundamental matrix. And then it shows you the theory behind it. It satisfies this equation, and then you need to plug in the values of this fundamental matrix. You have that here, and then the inverse of the fundamental matrix evaluated at 0. And we multiply that out and simplify, and we get this. This is the normal. Okay. So one of these is normalized. It wasn't clear which one. Okay. So this is the normalized version originally of the fundamental matrix. Now we're computing the actual fundamental matrix here. And then we use that. We use that to get a particular solution. So the particular solution is the fundamental matrix multiplied by v of x. And we're going to plug that in. This is going to be kind of an ansatz, and we plug that into the original equation. First of all, take a derivative, find the derivative, and then we plug in that formula. And we plug it in on the right-hand side as well. And then because we have values for these things, we can simplify, cancel like terms, multiply by the inverse, and then we essentially, it's showing you the formula for what you need to do to compute the answer, and just plug everything in, and you get this, and you plug in the forcing function, and you get this answer for the particular solution. And then we plug that back into the general solution. So we had these as our solutions for the homogeneous solution. And we would have to plug those in here as well to get the actual values for the general solution. So the homogeneous solution plus particular solution. Okay, there's also a kind of sub package for reducing order if you can't solve ODE completely, but you're looking for particular solution, or there's two other commands. If you can recognize that the ODE does not depend. So I was just talking about there's two different algorithms. If the ODE is recognized as not depending on the dependent variable explicitly, but just its derivatives, then you can do a change of variables. The derivative becomes your new variable and solve that reduced order ODE. And then once you've done that, you do the change of variables back. There's an equivalent kind of algorithm if it doesn't depend on the independent variable itself. You can kind of switch the variables, make the independent variable your new solving variable. Kind of instead of having dy dx, you essentially change it into a differential equation involving dx dy. And solve it in terms of x and y. And then when you've got the solution, you invert that transformation. So I won't go into details on those, but the linear particular solution is, I think, very interesting for this audience. So here's an example of a differential equation with a given particular solution for the this is the solution for the homogeneous part of the equation. So y prime equals essentially y double prime equals y. Let's say we have this particular solution. How can we use this to reduce the order of the differential equation? So we use this command linear particular solution. And what it does is it finds a reduced order differential equation that's essentially using this one to find a lower order equation that can be more easily solved. And it shows you the transformation that you need to get there. So you don't change the independent variable t and x are the same thing, but you would need to use this transformation. So it's introducing the new variable as the derivative, the total derivative of y over e to the x. And how did it know how to do that? Well, I'm not sure we can do steps here. But before I go into that, I'll just show what we can do with this. So we solve the reduced ODE and get this solution. So this is the solution in terms of u of t. And now we plug in this transformation again. So we use that transformation and we get a reduced order ODE for the original equation, but in terms of the same variable, same solving variable y of x. And then we can solve that using some other method. This looks like first order linear, so that's it's quite simple to do. And then that's the solution for the original equation. Now you can also give the solve option for the linear particular solution command, and it will just go to that answer directly. And it's not expanded, so you need to expand it to get and simplify. Do that here. So you can see you get the same solution as above. And then there's another option. So get the solution, but also output in terms of the basis. You can see that the basis here is e to the minus x and e to the x are the two particular solutions, independent particular solutions for the homogeneous solution. And it's producing those. And then the particular solution for this non-homogeneous equation is minus x. Y equals minus x. And then if we just show the new solution, it looks like this. And we can compute the Wronskian. It's just some commands that are not as part of the student ODEs package, but they're elsewhere in Maple. So this is the vector calculus package. Compute the Wronskian and and then also the linear algebra package. We have a determinant command, and we take the determinant and simplify it and returns 2. And that's showing that these are independent solutions. If they were dependent, then it would return 0. And yeah, this is just showing that if you add an extra variable here, you can choose the name of the dependent variable in the reduced ODE after doing the transformation. I just want to go nearing the end here, but I want to go show some more interesting visual commands. So here's a system of 2 ODEs. I've got a range for the y and the x values for the dependent variables and a range for the independent variable. I've got a parameter value, k is equal to -1. And I've got these are essentially initial points where it's going to draw the solution curves through those points. So let's see how that works. So it produces a direction field and some solution curves, and each of those solution curves is located they go through the points specified by, you can see x. If you choose this first condition, x would be 1 and y would be 2. So we look on the graph, and if you go to where x is 1 and y is 2, that's near the top. So I'm trying to get this all on the screen. So that'll be up here somewhere. And then at the same time, the t value is 0. And you notice t was changing from 0 to 5. So it's essentially putting a solution curve starting at t equals 0 and going to t equals 5. And this is interesting because you can click on here and it'll add more solution curves at wherever you're clicking. You can also adjust this manually. You can adjust the ranges of the things you want to plot. So if we want to go for -10 instead, we can just do that. Let me see, I think there's a button I need to press. I just need to click somewhere outside of where I was typing, and it'll replot it. You can see my solution curves are all shifted over because I expanded the horizontal range. I can change the parameter value. You can see, let's see how that would affect the plot. And it's changed it somewhat. Maybe if I do a bigger change here, it'll change it a bit more. There. You can actually add, you can just type in your equations and change the system as you like, and press the update system button, and that hasn't done much. Let's see if I put a factor 10th here, see if that changes something. It's gone the wrong way. Yeah, you can see that's had an effect. Anyway, you can adjust everything, clear the initial values to get rid of your solution curves and add more of them by clicking, and so on and so forth. Now, we did a custom system, but there's also a drop-down menu here, and there's a bunch of standard systems that you can play with. So the damped harmonic oscillator, you can see it's kind of circular motion, but because it's damped, everything's going towards the middle and eventually settle down to a stable point in the middle. And there's various things to adjust there. You can just, this is an example from medicine, malignant tumors, the Lotka-Volterra model, and so on and so forth. Van der Pol oscillator and housewarming model, so forth. I think that's basically all I wanted to show. Just one extra thing, you can just call OD plot with no arguments, and it will just give you one of these. It'll start with the damped harmonic oscillator, but you can get all those other systems, and you can, of course, adjust the system yourself and plug in your own custom system. I think that's all I wanted to show. You know what? I wonder if I go back to the top, I can show the help pages now because I'm showing my whole screen. Rochelle, can everyone see this now?
Yes.
Yeah. Okay, so this is just a list of all the different commands in the D tools package. See, there's a lot of them. What else did I want to show? Desolve. It's useful to go through desolve and see different types of things you can do. Student ODEs. You can see it's categorized into, what type of commands they are. You can see there's a lot of different types of commands. The thing I wanted to show is OD advisor. Here you can see Maple has a large class of different equations that it's solving algorithms that it knows how to solve. PD tools. There's a bunch of different commands for dealing with partial differential equations and systems and so forth. That's more advanced. Yeah, I think that's all really I can think of to show.